Good morning. Welcome back. I'm Jan Hichu and I am busy unpacking IESve through a number of short videos. And we are now going to look at the use of IES to analyze the light quality or the natural light quality within the design of the building that you are modeling. There's quite a number of tools, so I'm only going to cover two very brief or small parts of it that really only considers natural lighting. But for any of the interior architects, there's also a very rigorous set of tools where you can model the use of electric lighting, which I think, well, it's not only for the interior architect, I think for architects as well. That's something that's often quite difficult to be sure about. And I think this is at least one of the methods that you can start modeling and assessing what the ultimate light quality would be if you have a selection of luminaires lighting up a space. We're not going to cover that. We're only going to cover Flux DL, which is used to calculate daylight levels and illuminance within a space. So we're looking at what happens due to all the glazing we've got within a space. And then we will also look at Radiance IES, which starts looking at illuminance again. It's a bit more rigorous. It starts looking at it from a person's point of view, and then ultimately gives us more insight into glare, which I think is valuable. In this video, we'll only really cover Flux DL, I think, as a good start to give a good basis of the space itself that we are working with. So again, you can do this analysis without going through the initial protocol that I've defined. So, the whole modeling the site, locating the site, and then going through all the inputs and so forth. What is critical though is you do need geometry, as you can see. So the building must be, or the space must be modeled. Then it must be located. The weather file is not as critical here, but the actual longitudinal and latitudinal position is really important. What that points out, though, is certainly you have to look into the implications of overshadowing that takes place. And I haven't done detailed analysis of that yet, but you can model surrounding buildings and see whether that actually adjusts the indoor light quality, which makes sense. It should, if you want to represent reality. So something to just consider. But like I said, you must have the geometry ready. It must be located. I'm using the model that we have been using, so you'll see that it is correctly located, and we've got the geometry we're using. Good. So what is the process that one follows with Radiance? Or with Flux DL, not Radiance. First of all, I find it easier to work in the scale of a single building, a single space. I find it quite difficult to think of it as a whole building, so I typically would go down one level so that I can choose the space. Now suddenly the model changed dramatically, as you can see. So we've moved down one level, and immediately I only see the illuminous plane there. And if you want to see what we are actually working with, you can simply go to the top where you can adjust surface or illumination. So ultimately illumination shows what we will be assessing. Because we're looking at the whole space, we're not looking at vertical planes and so forth. Um, um, we are going to therefore assess that floor plane that you're seeing there. But if you want to just keep track of where you're at, you might want to simply choose to show the whole model. Down at the bottom, you see an information bracket, a tab that gives us the general information of that floor and then the lighting parameters. You'll see that it defines the work surface as 850 mils. That's generally what we use to calculate lux levels. Now remember, lux levels are known as illuminance, or illumination, and it is, let me just show you here, illuminance, which is effectively assessing the light quality at a certain work level. So we typically define it as 850, and it's measured in lux. we can also in this model also assess the the luminance, which talks about the light source itself. But if you're looking at daylighting, I don't quite see the sense of that. So why I note that is important is that work surface can be different. If you are working in a specific context, let's say you're working in a Japanese context where you might be, or a Hanuk context where you're working at about 400 mils above ground level, then certainly 850 isn't a good surface, and you might want to lower that level. But for general standards and regulatory purposes, we simply keep the 850 mils. And that's how we generally measure lux levels and how you then define and assess whether your lux levels is correct. You'll also see here that you can define the height of what we call the false ceiling. That's the ceiling plane effectively. That gives us an idea of the floor to ceiling height. It can be similar to what the building is modeled at, but you can define it as something differently. And then ultimately, you'll see that I can also adjust the actual reflectance of that ceiling, which 70 is generally a good figure to use for a whitish um, surface. But you see, there's also ways that one could actually start defining it more specifically. But generally, just a good basic to check beforehand. Um, good. So once you have defined, if you've set up your model, so you know that it works, you might actually want to go and define the surfaces within the space, because that's actually what takes IES a little bit further than any of the other programs. Is that you can now go and say, well, what's the nature of the floor, the wall, the ceiling, the glazing, and so forth. So you'll click the surface properties here, and you'll see here, if you've selected a surface, then then you'll see what the options are that you can use. So you can use the floor, the ceiling here. Should you go and choose the whole the whole building form itself, so we go up one step, then you can actually choose what the nature of the ceiling will be, what the nature of the roof would be, and so forth. And that's actually quite helpful. That helps you to assess. So obviously white walls can actually make a difference if in the interior rather than black walls. As we all know that the reflectance and absorptivity makes a big difference. If you don't quite understand these terms, please go and look at your previous Earth Sciences notes and that I've shared with you in the class. So you can then say, okay, wait a minute, I think this building isn't, I don't want to take the typical default surface, so it's transmittance of, well, that's for glazing, so we will not, but it's for walls, inside reflectance of 50% and an outside reflectance of 10%. Um, Essentially, what we're considering here is 50% reflectance means it's not a completely crisp white wall, and so it's just a good basic decision to make, like a beige kind of wall. You can go and say, no, no, I think we would like to, for the wall, for instance, make it a glazed tile. And you can adjust that, which means you can choose, like I've done, show you here again, you can choose what it is and you can place it, which immediately the reflectance changes to 80%, which is certainly a dramatic difference. Um, and similarly, if you choose to go for a very dark grey concrete and you replace that, you end up with a 20% reflectance. The other option is to simply change it here, to say, no, I think this should be a Vanta black reflectance, so 5% reflectance. It should be the darkest possible wall you could ever imagine. Um, and there you've gone. You've done that. You've now adjusted that surface, which means you can now actually, and so you can go through the whole process. You can adjust the roof surface in the end, or the ceiling inside, to a no fines concrete. I would suggest that you keep to what is defined, like a good basic. But nothing stops you from playing around here and testing that. Apologies for that sound. Let me just switch that off. Um, but but either way, so you can actually define the surfaces inside to give you a good to define the indoor spaces in terms of how it now starts reflecting and adjusting the surface quality that you're now actually going to assess in the process. So you can go in more detail there, and there's multiple options of defining it for the whole building or for specific spaces. You can then go through the analysis calculation. So I don't know. I would like to define that button, but I'm not sure what it looks like. But if you find the analysis calculation button, like I've highlighted there, you can click on that. And there, I would suggest don't mess around with anything you don't know well. The basic setup is a basic assumption that one would typically take. So should you start understanding ray tracing and so forth, then you can go into detail. But so I would simply say use the point-to-point radiosity. You'll use a simple planar analysis. The margins, you'll use the SIPSI value, um, which I do think is correct. You can change the amount of detail that that model needs to have. Obviously, it'll make a difference. So your grid size, you can also change. It's 0.5, so it's half a meter. I would not start there. I wouldn't change that yet. I would first just check whether your model works, whether your parameters work, and then if you really need to add more detail. And then really important, you need to define your daylight. You can choose to have a clear sky, for instance. The reason why we choose overcast, and you can simply keep it as it is that if you look at daylight factor has a general standard that we consider daylight factor. If you don't understand daylight factor, please go and have a look at the notes. It talks about the amount of light inside a space and talks about how much additional light we'll actually need. And it's typically assessed using an overcast sky. So I would, again, not change it, just keep it. And then if you press OK, you'll start with your analysis. I'm going to press OK and I'm going to pause the video because it takes a little bit of time, but it actually then models the whole space based on what you've selected in the process. Okay, so I'll press OK and it starts, and then I'm going to. Good. Okay, welcome back. So we've just concluded the simulation. You'll see slowly as your simulation runs that that Illuminance plane that I've showed to you, that you've now selected and you're working with, um, will be colored in. So you'll slowly start seeing how it analyzes it. And then you'll get this first screen, which is a summary of the analysis. And you'll see that I've done a few summaries already, so it shows the previous summaries in there, um, and you see it gives you a basic analysis. So you can see the floor areas. Well, it's just the basic analysis of the building itself, and then you can go down to the floor that we've now tested. Remember, we've selected to test floor 2, and we can see floor 2. If you look at the general daylight factor, we've got an average of 4.8%, a maximum of 21%, and a minimum of 6%. What that means is generally we're about 5 in terms of daylight factors. And a daylight factor of 5 or 5% is accepted. It's actually quite good. You can see the uniformity being defined there, and the diversity, it's quite low. And if you look at the actual floor itself, you'll see what the implications are. So there are ways that you can present this so that it's easier. And um, I'll show you how to view other aspects as well, but let's start with daylight factor. Okay, so you can then choose to use a filled contour. I think it's sometimes a little bit easier to read. So you can see the 21% is right here on the eastern side, where we know we've got lots of glazing. and 4 is a large portion of the room, with that western edge being much darker. You can also choose to use numeric grids. So if you go inside, you can see, oh, that's 0.6 down there. The average overall daylight factor, where, down here we've got 2.25. So on the grid pattern of 0.5 by 0.5, you'll see that that it has actually calculated for you. So you can actually define and find the dark spots very clearly. And you're welcome to look at, there's a number of other ways of presenting it and representing it, so that it makes sense in the end. You can also define the threshold above which it should define. So anything at the moment, the threshold is 0.2. So if you apply that, oh man, we have to I have to show it to you again. Daylight factor. Now it's disappeared altogether. Okay, let me try and find. I might have to run the simulation again. Okay, so I'll pause it and then get the simulation going, and then we'll continue again. Okay, good. I found it. For your reference, I think this is good to note. If you ever experience this and it disappears, it's because you haven't selected the space. So you simply select the space again. But what we're saying here in terms of using a filled threshold, you can say, well, let's say anything with a, a daylight factor above 4, where are those? And if you apply it, we can see, okay, that's where all the daylight factor above 4s are. If anything above 3, for instance, we'll have a slightly different threshold. So you're welcome to explore it. There's multiple ways of viewing the assessment that's been done. There's something else that we also assessed, and that's the illuminance, which I think is important. It tells us there, if you look down here, it says, remember the illuminance is now at 850 mils above the finished floor level. The minimum illuminance is 71. Now we know, so you can go and look at SANS. There is a SANS standards for that specifically. I'll share the note with you. I believe it's section O from 10400, but there should be another SANS. It's also very, very specific. I'll share the note with you. But you'll see that 74 is way too low. It's often very few rooms that actually has that. But we'll see that a lot of it on average is about 580. It's good. But we see the maximum also being really high. So there is certainly a problem with that eastern glazing. And if you adjust this and you say, well, I don't want to look at daylight factor, I just would like to look at daylighting, then you'll see my if I choose daylighting under this little section, you'll remember to choose the space again. I'll see that my index now changes, and I can actually now assess it. So I can see, okay, wait a minute, this is where the lux levels are assessed for the various spaces, and we can again use the same method. We can again say, okay, let's take a threshold, and we'd like to assess any lux levels above 300 and see which part of the, and clearly we can see again there's a dark spot in the center. So but if we look for anything, I mean, lux levels are also problematic. Anything above 1000 is really uncomfortable as well, and we'll see that this eastern area is really problematic. Okay, so two really, I think, interesting ways that you can assess it. The one is to use the report that's provided for you, and you can go through these reports. There's a lot of extra information that it's presented in different ways. Similar information, it's again a daylight analysis. So you can choose whichever one you want to. This could be a printed report in the end. Or you can use the graphics themselves. There's ways that you can save the bitmap, but you can also simply just select do a screen grab if you need to. And finally, you can look at the luminance, which we said is the candela per square meter. But As I noted, that's actually a light source. It's about how much light it presents for an area, and it's actually not for daylighting. It's not actually helpful. So the two things that Flux DL is really good for, that you can use it for, is the use of it for daylight factors and the illuminance, so you can understand the lux levels within a space. Obviously, as you start changing the windows or the nature, the quality of the windows, as we noted there in the beginning, the surfaces and so forth, then it changes. And that's also something that's actually worth exploring. Good. So the next video we'll look at radiance, which would be a person's perspective of it, but this was really looking at the space itself as an overall analysis. Thank you.